zip tại do mày vậy?
Mua hành đó.
We already okay.
Okay, that's good. Yeah.
All good. Wonderful. Great. If you're ready, let's get started.
Thanks. So before to start my talk, I would like to take the opportunity to thank all professor and panel and all my friends that spend your valuable time coming today. And welcome to my confirmation presentation. So the topic today is development of an advanced computational approach for early warning and prediction of rainfall-induced slope failures. So this is the content for today, including 7 sections. First, introduction. So rainfall-induced landslide is one of the most common serious natural hazards for hilly slope due to prolonged or heavy rainfalls. It may suddenly occur with high traveling speeds, posing threats to human life and properties, including building, highways, and infrastructures. So how has this disaster happened? Basically, we have a slope, the water infiltration into slope due to heavy rainfall, and it makes the soil become saturated with water and loses its strength. And this means it can no longer support the weight of overlying material, and it becomes unstable and starts to slide downhill. We call it landslide. Osanai et al. 2009 here, they conducted statistical study on 19,000 cases of landslide, and they reported that 93% of those landslides was caused by heavy rainfall. According to International Disaster Database, more than 62,000 deaths with a total loss at least 9.7 billion US dollars seen from 20th century due to the rainfall due landslide. And furthermore, global climate change had triggered high frequency of rainstorm together with fast population growth with improper settlement development. It makes this disaster more and more harmful impact to the community. So for us, like academy or geotechnical engineer, what can we do to minimize this problem? So among various methods, the monitoring and early warning system are considered to be one of the most promising ways. So this is the illustration of the rainfall-induced landslide early warning system that you can see over here by Uchimura et al. 2015. 2017, Carlo here, he plotted the components of rainfall-induced landslide. In here, I want to highlight that when we're talking about this system, they have the technical part and the non-technical part. Example of non-technical part is communication and distribution. It means how you send the message to the community and how do they understand. Emergency plan is when a disaster going to be happen and what the people should do. So in my project, we focus on the technical part and we make this research question. So with the input information, such as soil properties, water pressure we get from sensors, we generate the initial condition, and with the rainfall data we get from the rain gauge or from weather forecast. Example, 2 weeks, how can we use the advanced computational approach that can predict when, how, where that disaster occurred. So in here, we want to emphasize the information of beyond the onset of failure. It means that we can detect when the failure happened, and we also want to know that the destruction zone, what's its impact to the community. So literature review. Firstly, let's answer the question, how has rainfall-induced landslide been modeled? Commonly, the traditional LEM, FEM may be two of the most universal tool to study. Example you see over here, 2017 Zhang et al. Simulate the rainfall of seabed analysis by the finite element method, and they're using the information incorporated into LEM over here to calculate the factor of safety or also estimate the critical slip surface. 2021 Citandreas over here simulate the rainfall-induced line. In here, they also incorporated the advanced unsaturated consumer model, and their prediction compared with the sensors on the field, but then they can detect the failure. So it has been successful in several practice applications, but it should be noted that it has some limitation. The well-known issue named mesh distortion. So the limitation I want to highlight here is most of the efforts of both, they have been limited in the failure initial stage. That is where we have small deformation. So from the point of view, to overcome the mesh distortion issue and simulate large deformation problem, the method over here, MPM, PFEM, or HVX, the smooth particle hydrodynamic, a mesh-free continuum method, might be a better choice. It has been proved that this method that you see over here have great capability in dealing with rainfall new landslide with large deformation. And I also would like to emphasize in here that each of the numerical tools, they have their own advantages and disadvantages. No method is better. For example, if I'm looking for the safety design, I could definitely choose the finite element method in previous slide. But if I'm looking something extremely large deformation, then I could have the option of MPM, PFEM, or HVX over here. And in this project, based on our resources, the fully validated HVX framework is selected and continue to develop. And in here, I want to show you something for limitation. Currently, still lacks the incorporation of advanced quantity model to properly simulate unsaturated soil behaviors. The second limitation here is these studies above here are deterministic without considering the geotechnical uncertainty. So it's meaning that the spatial variability of soil properties, it may significant effect to landslide failure, landslide property, and risk assessment. So how has the geotechnical uncertainty been considered in rainfall landslide modeling? First, take a look to this picture. So slope profile of the natural slope are unlikely to be completely uniform due to the complex deposition and alteration process. So even with so-called homogeneous soil layer, soil property tend to vary from one location to another, and we call it the spatial variability. So the first pioneer work we can name is from Professor Fenton and Griffith over here, 2008, when they incorporated the random field into the finite element method to have the Academy of Geological Engineers to do the slope analysis. After that, doing for rainfall new landslide analysis, more of the work focused on the one dimension of random field, and they're using it to calculate the factor of safety or also the failure probability. In terms of numerical tool, Nguyen and L over here, 2019, they're using the finite element method to use with random field to simulate the rainfall over here, and they again incorporate the water pressure into the LEM method to estimate the factor of safety, also critical failure surface. So all of the case I'm showing here is involved with a small deformation or factor of safety. When it comes to large deformation, the method MPM or HVH here is actually already incorporated the random field, but they currently using for granular flow without considering the rainfall. So when they want to dealing with rainfall new landslide, they still using the random field from finite element method. After analysis, they assign information to the material point and particle in the HVS over here. The limitation I want to show in here is, first, with our numerical tool we're choosing, we still lack the considering of spatial variation of soil properties. The second limitation, to address the challenge of the limited data input. So these studies will often use the Monte Carlo simulation to account uncertainty by randomizing 1,000 or 10,000 times to calculate the failure probability. However, this approach can be time consuming and does not provide accurate prediction of time of failure. Therefore, there is a need to find more efficient and reliable solution. And how to deal with the such field have limited input. So you can see over here, basically here we have the field data with 3 layers. So what we know about actually the field is the dimension and some of the boreholes data in the field. And we want to know what is the information of the other position borehole or the general slope. And this method, at least here, state-of-the-art, I make it 2 groups. So the first group here, the Chilazo method, is based on the optimization. They will showing you only one solution based on the minimum error or constraint they're using. The second group over here, they based on the uncertainty, which can give them the range of result that you see. And then they using generate the numerical field, and they compare with the black is the background over here to validate the method. So the limitation I want to show in here is With example, G-lasso method here is still need a lot of time to run. The second is these methods have not been well established for rainfall-induced smoke analysis, and this still lacking the physics data validation. So what I mean the physics data validation in here is, in the field we still have the monitoring sensor data. So if we can take advantages of the information to basically to refine our prediction. So finally, this is the biggest picture. So why we need to use the numerical tools? What is state-of-the-art of the rainfall-induced landslide early warning system, or how have the failure criteria threshold have been established? So here, after a lot of review and the state-of-the-art rainfall-induced landslide system in the world, in here, most of the systems currently rely on global rainfall threshold and the historical landslide. An example of here you will see in Brazil, based on expert and the local government, they decided to have 4 warning level. Each of warning level over here they have the rainfall threshold with that. In Vietnam over here, they are using the relationship between rainfall intensity and duration. In Southern landslide China over here, they're using the threshold with the formation speed. Move to Wollongong in Australia, in New South Wales. Then in here, they have the warning system, and they're using the condition between duration and rainfall intensity with the 3-level warning over here. And I also read through of the building code of the guideline of landslide hazard over here. Most of the document currently focus on the property of failure. And the limitation I want to highlight in here is the existing failure criteria still lacks the failure mechanism base. It means that they on how solid form, coupled seepage, flow deformation behavior, and runoff field affected to failure process. So from all of that, this is the gap in the answer summary in here. So first one, with our numerical tool we're choosing for study, lacks the incorporation of advanced model and needs considering the spatial variation of soil properties. For rainfall induced analysis, the tool to represent field conditions using limited data is still missing, and also need to take advantages of the sensor monitoring from the field. The third one is existing failure criteria lacks the failure mechanism based. So from our gaps, this is the AMW1. First, we incorporate the advanced and saturated quantity model random field into the state-of-the-art HPX. Second, we develop the novel algorithm to create suitable initial slope condition from limited data and using physics-informed random field. So finally, we combine all the tools together and we establish the failure criteria. So the contribution I'm really excited to share with you my project. First key thing here is this is the advanced knowledge and computational framework that can predicting entire rainfall induced landslide using the spatial, considering the spatial distribution and using the limited data inputs. Also, the key second thing here is this is a valuable tool, and the failure criteria we established from here can incorporate it to the current rainfall induced landslide early warning system design that can produce better warning, thus reducing the damage of structures and loss of lives. Proposed research plan. So in here, in my PhD journey, based on the gap, I make it 3 steps. The first stage, we incorporate the advanced model random field into HPX framework. Second, we reconstruction field data from limited measurement. Finally, we combine all of them together and establish the failure criteria. Research methodology. So first, we develop couple HPX framework with advanced saturated quantity model. So we start from the multi-phase mixture theory when we have the mass conservation equation, momentum conservation equation, and then by solving the equation, we get the increment of polar pressures, or by summation of all momentum equation of each phase, and we get the increment of velocity. And to solving the equation, first we need to stress-strain relationship by using this quantity model. We also need the degree of saturation and water permeability function. Finally, to solving the equation is this is the spatial derivative. This is the way that we need to using HPX. So what is the HPX method and how does it work? So the HPX method here is the mesh-free continuum method that can in which particle will carry the field variable and move with the material velocity. Second, we incorporate the random field into our framework. So what is random field theory? So random field theory here is mathematically framework that can model the uncertainty. So if you want to learn about random field, this is the two picture that you want to understand. The first one we call it a PDF, which is a probability distribution function. So in here, they will give you the information like central tendency or the spatial variability, which can represent by mean, variance function, or standard deviation. The next picture over here can show you the spatial correlation. We call it the covariant function. So after all of the things, we choosing the method, and we can generate a numerical field like this, and we assign to our particle in our numerical tool that we're choosing. So the final here, this is where we develop normal algorithm to create suitable initial slope condition for limited data. So when we make this question, what if we actually only have very few measurements of our system? So in here, I think I'm showing you one example. The first example, we have a blur picture, and then we want to know what is the original picture, or we just have to input like one ball, and then we want to know what is the whole field data. And in this case, it's a problem well known called the underdetermined problem. And in this case, that basically you have the input is just a small vector, but you want to output like the very tall vector. It means that you have the infinite solution. And to deal with this case, we're using an optimization algorithm to find a particular solution. So in our project, first we're using compression technique. In here, basically, we have the input limited, we do the optimization, we figure out what is the pattern, hidden chain in here, and we predict the output. And also the artificial neural network we will use, basically, this is a set of optimization can help us to improve our prediction. Preliminary research. So in here, first one, we validation with one dimension transient seabed flow. So in here that you will see, this is initial condition, this is the 3 meter xy column, the flux positive here represent for the rain, the negative flux over here represent for the sun, which is infiltration or evaporation, and we compare with the analytical solution. Next, we validate with the 2-dimension transient seabed flow against experiments. So this is the experiment setup from Keaton Ray 2007, and the list parameters here allow us to calibrate our soil water cavity curve. And first, we compare results with the finite element method. So you can see from here the excellent agreements between the two numerical methods, suggesting that our developed HV model could capture well the change in seabed flow, not only isotropy but also anisotropy. And next, you can see here we compare with the experimental data. So this result that you can see represent for the data, it location from 1 to 5. This represents over here. This is from 6 to 10. You can see from over here. So in next step, I'm going to show here is couple seabed flow deformation. First, we start with the advanced saturated quantity model, following the chill technique here with the Rillingen soil sample, and then we do the numerical test, compare with the experimental data to see the performance of the model, and we incorporate it into HBX. First, we do the simple test with the constant volume shearing, and then you can see over here the excellent agreement between the single element solution and the HBX solution over here that can prove that our incorporated is correct, and we start to conduct the large formation. In here, with the large formation case study 1, the validation against of Rillingen field experiments. Here, this is our model setup. The parameter here basically can have a calibrate soil water cavity curve, and this is our result that we get after the rainfall, and then we have this collapse, and we compare with the experiment, we compare with the sensor on the field here. So in here, the green line represents for the HBS solution, the red over here represents for the sensor that you see over here, and we also capture question 9 with the displacement evolution. The second validation case here, rainfall new landslide experiment from Denzel that you can see over here. Then this is our model setup. And again, parameter here can help us to calibrate our soil water curve. And this is the result. So in here, after rainfall, we compare with the suction evolution and also the detect when the failure happened Also in here, we can detect the final runout distance compared with the instrument that's out here. So the final result, that's a really interesting, like the other part I want to share here is reconstruction random field. That is a way that we're using the optimization. We start from some simple signal with a limit data input, we reconstruct it. Also the friction angle with haze that you can see over here. And then we start with the slope, the numerical field. So basically in the field, we did one borehole. And basically the information from the field we didn't know, we just had one borehole information. And then from this information, using optimization, we predict the other place in the field. And then reconstruction with our solution, we compare with the neural field that we generate basically to evaluate our result. And then 1 ball, 2 ball, 4 ball, 5 balls. The more ball information incorporated, the better of the solution that we can have. And then we also incorporate in here with the slope with 2 balls, we reconstruct here. We also set up some sensors basically to take these advantages to doing my next step. So I take the information to make the prediction better. Timeline. So this is the work I'm doing in the past, this is the work I'm doing in the future. Acknowledgement. First of all, I want to thank all my supervisors, especially my supervisor Hamud for endless support. Also, not only study but also life. Thank you, panel members and my friends that spend your valuable time with me today. I'm so grateful.
Great. It's great, Tom Edmonds, for the presentation. We come to the German audience question. Any questions from your friends?
I can have
All right.
Thanks. Thank you for the fantastic presentation. So you mentioned that your object of your project is to develop a failure criterion that can be used for engineer design for rainfall-induced rock failure. But to my best understanding is that to develop a criterion, you need a lot of data or case study. So if you don't have that much data, how can you make sure the criterion you develop is reliable or meet the engineering standard?
Yep.
Thanks.
Yes. So thanks. That is the case that we want. That's why we start from the numerical field data we generate. So we call it the hidden layer that you see over here. So normally the field is limited, right? Correct? But in here, because we start from numerical field, then we have the data already. It's basically hidden, and then we're using our development solution to basically validate our solution.
So you mean so you mean you using your numerical methods do a lot of simulations that adds to your data to develop your criteria?
So that's that you can see from this slide over here. That is where we generate like the field, incorporated with random field, because in the actual field, the solubility distributed, right?
Yes.
And that's why we generate the numerical field that represent of the field to evaluate our resolution.
I see. Yeah. Thanks.
Yeah, thanks.
Finish.
Any further question? Because have we been not that probably is online audience. Any questions? No. Okay, so probably move to the next